Welcome to lecture 6.5 on matrix products and inverse matrices. Okay, we had the inverse of a matrix before, and today we're going to look at the inverse matrix of a matrix. It's a little bit confusing, but we'll explain that as we go through. To understand the reasoning behind the definition of matrix multiplication, look again at the Easy Life Company. This is the problem we started chapter 6 with. Suppose sofas and chairs of the same model are often sold as sets, with matrix W showing the number of each model set in each warehouse. For example, sofas and chairs of model A, there are 10 sets in the warehouse in New York. Let me get my pointer here. There are 10 sets of Model A in New York. There are 5 sets of Model A's in Chicago. And there are 4 sets of Model A in San Francisco. If the selling price for Model A set is $800 and the Model B set is $1,000, and the Model C set is $1,200, find the total values of the sets in New York warehouse. Well, this is pretty simple, right? We have 10 sets of Model A, so 10 times 800. We have 7 of the sets of Model B, so 7 times 1,000, because each set is 1,000, plus 3 times 1,200, because we have 3 set C sets. Okay, and then we just sum those together. And you can see that here, okay? Pretty simple, pretty logical if we're trying to find the value of all the sets. So in New York, for example, in the warehouse, they have $18,600 worth of Model A, B, and C sets in their warehouse. Now we could use matrices to solve this as well, specifically a matrix product. Okay. We had the matrix given to us in the previous slide. If we create another matrix with the value of matrix A, matrix B, and matrix C in a column matrix, then we can do what's called matrix multiplication or a matrix product. When we multiply the matrix of the number of sets times the price matrix, what happens is we get the value of the warehouses of all warehouses. What happens is in matrix multiplication, you'll see that you take the row of the first matrix, the row of the first times the column of the second. So when we're doing the warehouse matrix times the price matrix, it's the row of the warehouse times the price of the each set. Row times column. If you remember, the order of a matrix is row by column, which we use the letter X to represent by when we're doing, for example, the area of a room. It's, length by width, or LXW. So it works out intuitively because we use the letter X for multiplication. Row times product, and then we sum them all as we saw in the last example. So 10 times 800 plus 7 times 1,000 plus 3 times 1,200 gives us the value of matrices, the value of furniture sets in the New York warehouse. Okay. The order of a matrix, as I mentioned, is a helpful reminder, row by columns. And what we do is take the rows of the first matrix times the columns of the second matrix. Okay. So what I've done here is I've transposed that row into a column so it's easier to see. So take that row, turn it into a column, and then multiply across, and then add all of those products. Okay. So by doing this matrix multiplication, the warehouse times the price, we can actually find the values of the matrices in all 3 cities, New York, Chicago, and San Francisco. Okay. when we're doing the second entry into the answer matrix, again, we take the second row times the column, so 5 times 800 plus 9 times 1,000 plus 6 times 1,200. For the third answer, we get 4 times 800, 8 times 1,000 plus 2 times 1,200, and you get all of these matrix answers. Okay, again, here I'll walk through it. So it helps me to kind of, and sometimes I'll even do this on scratch paper, take a little sticky or something and write these as a column right next to the columns that I need to multiply. And then I can add 10 times 800, 8,000 plus 7,000 plus 3,600 gives me 18,600. For the second entry, I take the second row. This is for Chicago. Again, 5 times 800 is 4,000 plus 9,000 plus 7,200 gives me 2,200. And then for the last matrix, for the last entry, I take the last row, turn it into a column, multiply across, and add 3,200 plus 8,000 plus 2,400 gives me 13,600. Okay, so again, what we're doing here is we're taking the row from the first matrix, the warehouse matrix, times the columns in the second matrix, which is the price matrix. In order to define matrix multiplication, in the general case, we first define the product of a row of a matrix and the column of a matrix with the same number of entries in each to be the number obtained by multiplying the corresponding entries, first by first, second by second, etc., and adding the results. Again, another example, here we have a row matrix times a column matrix. So we'd get 3 times 4 plus negative 2 times 5 plus 1 times 0. We'd add them all up, and so this matrix would just give us the matrix 2. Okay. So here, let me say that in a little bit simpler way, I hope. So when we have matrix A times matrix B, the first thing we want to do is check to see if matrix can be multiplied, okay? So what we're going to do is compare the order of each matrix, and notice the inside numbers must match. Now, what does that mean? Well, if we have matrix A here, which is a 2 by 2 matrix, 1, 2, 3, 4 are the cells, and matrix B, which is a 2 by 4 matrix, 1, 2, 1, 2, 3, 4, 3, 4, are the members, or elements. So matrix A is 2 by 2, and matrix B is a 2 by 4. These are the orders of the matrix. And notice the inside numbers must match. Make sure you put them in order. This is A times B. So we have 2 on the inside and 2 on the inside. Okay, the inside numbers, when you put these matrices side by side, 2 by 2 and 2 by 4, the inside numbers, which are in red here, must match. If they match, you can multiply these matrices and get an answer. If they don't match, you cannot do matrix multiplication with these matrices, and there's no solution. The answer, to determine the size of the answer matrix or the degree of the answer matrix, you also compare their order. The outside numbers are the order of the answer matrix. So in this case, our answer matrix, the outside number is 2 in A and 4 in B. So our answer matrix is going to be a 2 by 4 matrix. So we're going to have 8 entries, okay? Again, looking at it a different way, the inside numbers must match when you look at the order, and the answer, if these do match, then we can find the size of the answer matrix by looking at the outside, okay? Another thing that happens, remember that the position of each element in a matrix, for example, here in matrix B, the first element is row 1, column 1. So this would be lowercase b 1, 1. That can give us a hint, because what that means is we're going to take the row of matrix A, which is row 1 of matrix A. Remember, this is a position 1, 1. So we're going to take row 1 times column 1. row 1 of the first matrix times column 1 of the second matrix. Let's go down over to this this member here, this 3, which is in the second row, third column. So this position would be lowercase b 2, 3, right? Lowercase b. So the second 3 here is in position 2, 3, second row, third column. So what we're going to do is take the second row of the first matrix times the third column of the second matrix and multiply those and add the numbers. So the matrix order and the element subset, or the digits that identify which element it is by row and column, second row, third column, tell us which row and column that we multiply by. Remember, it's always the rows of the first matrix times the columns of the second matrix, depending whatever order we're multiplying these in. Notice we could have a product BA, which would be totally different in this case. Okay, so the order that we're multiplying, A times B, is very different than B times A. So that's one thing to note, etc. But again, the position of each answer will tell you which row and column to multiply by. Again, for this 3, since it's in row 2, we're going to take row 2 from matrix A, and it's in column 3, and column 3 from B, and multiply those to get the answer for the answer matrix. We're going to do some examples, etc. Find the product CD when C equals this 2 by 3 matrix, -3, 4, 1, 5, 0, 4 are the elements, and matrix D, which is a 3 by 2 matrix with elements -6, 4, 2, 3, 3, -2. The first thing we're going to do is check that the matrix can be multiplied. Since matrix C is a 2 by 3 and matrix D is a 3 by 2, we check that the inside numbers match, and they do. They're both a 3. So we can multiply these. Notice that the size of our answer is going to be the outside numbers, so our answer matrix will be a 2 by 2 matrix. All right. So to find the first position in row 1, column 1 of the answer matrix, we're going to take the row of the first matrix times the column of the second matrix. And you can see those there in blue and it looks like a reddish color. Remember that we multiply each coordinating member. So -3 times -6 plus 4 times 2 plus 1 times 3. Add them up. And this gives us our first member of the answer matrix. For the second entrance, row 1, column 2, we're going to do the same thing. Here we're going to take the row of column C, the row of matrix C times the second column. The first row of matrix C, the second column of matrix D will give us the answer matrix in position 1, 2. I'm going to, again, -3 times 4 plus 4 times 3 plus 1 times -2. Make sure you do the multiply. I don't like that there's not parentheses in this example. There should be. Remember, you do multiplication before you do addition. You don't do this left to right. When we do that, we get the answer of -2. We can do this for the element in position 2, 1. And the element in position 2, 2, and we get -18 and 12. And so here is again, our final answer matrix, which is a 2 by 2. Again, when I'm doing the answer for -18, I'm in the second row and the first column. So I take the second row of matrix C, which is our first matrix, because we're multiplying C times T, not D times C, times the first column. Okay, remember this position in the answer matrix, -18, is in position 2, 1, second row, first column, and that tells us what we multiply. Position 2, 1 says multiply the second row times the first column, and then of course add them all together. I know it's a little bit confusing. Do a few of these until you do a few simple ones until you kind of get it down. All right. So let's look at a problem. A restaurant has a main location and a traveling food truck. The first matrix A shows the number of managers and associates employed at each. The second matrix B shows the average annual cost of salary and benefits in thousands of dollars. Matrix A has elements 5, 25, 1, 4, and is a 2 by 2 matrix. Notice that the managers is the title for the first column, associates is the column title for the second column, and tells you how many people are employed at each establishment. The first row is restaurants and the second row is food trucks. Matrix B is talking about excuse me, how much each of those people get paid on average. Managers earn an average salary of $41,000 and benefits of $6,000 a year. Associates get an average salary of $20,000 with $2,000 in benefits. So this makes matrix B into a 2 by 2 matrix with elements 41, 6, 20, and 2. Again, always reading across, doing rows first, and then the elements of each column. The first thing asked us to find the matrix product AB. So this is simple. Your calculator will also do this. You can enter in matrix A into your calculator using the matrix button, creating a 2 by 2 matrix. Then do matrix B, another 2 by 2 matrix with these elements. And then you can simply go back and select matrix A times matrix B, quite literally and intuitively, to find this. It's a good idea for you to practice doing these because on the test you will have questions that ask you to find a single member and then you need to show work or to explain how you got it. So when we do matrix AB, we get 705, 80, 121, and 14 as its elements. Okay, so that's the answer to part A, which is our matrix product AB. B says explain what AB represents. This can seem a bit confusing, but if you go back to what we remember about how we do matrix products, this can also help us interpret the matrix answer to a multiplication problem. Again, remember we're using the rows of the first matrix times the columns of the second matrix. So what we're going to do here is we're going to use the titles of the rows in the first matrix for our answer matrix and the column titles from our second matrix. So use the rows of the first matrix for our titles and then use the columns of the second matrix titles. Now it's easy to interpret. So again, that order of degree, rows by columns, can help us out. When we're trying to figure out what our answer means, use the titles from the rows of the first matrix and use the titles of the columns for the second matrix. So what this is giving us is the total salaries for restaurants and trucks and the total benefits for restaurants and food trucks. Basically our total human resource costs, because this is based upon how many people work in the restaurants and in the food trucks and by what type. Okay. C is pretty simple. It just asks us what's the total cost of salaries. Well, all we have to do is add these now down and benefits. So that's a pretty simple answer. I'm not going to go through that. That's just interpreting it. Okay, let's do a couple more problems. Let's find the matrix B times A. Now be careful here. A lot of times this is something students will miss because the matrix A comes first and they'll just try to do AB. But it's telling us to find B times A. And remember, the order is very important in matrix multiplication. Since B is a 2 by 3 matrix and A is a 2 by 2 matrix, Notice the inside numbers 3 and 2 do not match in this order. If we had put them in AB order, we would have thought we had an answer. Okay, so the order is very, very important. For any matrices A, B, and C such that all the indicated sums and products exist, matrix multiplication is associative and distributive. Okay? So if we can do A times B times C, where B times C is first, then this is the same as if we do AB first and then times C, or A times B plus A times C, or AB plus AC, or B plus C times A equals BA plus CA. It's just saying that the associative and distributive properties work if all the products do exist. Okay? Again, here I'm going to remind you that the order is very important and that the matrix A times B does not always equal the matrix B times A. In very rare cases it will, but it's very rare that these are the same answer. Okay? You have to pay attention to the order that you're multiplying things in. You have to check to see that you can multiply them by the order of each matrix and the inside numbers. And then remember, the outside numbers, if it does exist, will give us the size of the answer. All right, identity and inverse matrices. These are very important, and you have to solve some problems using these. Recall from section 1.1 that the real number 1 is the identity element for any multiplication of real numbers. This just says that if you multiply a number by 1, you don't change the identity of that number. 4 times 1 is still 4. So that's why it's called the identity element, because you don't change the value when you multiply. It's the multiplicative identity element. For any real number, A times 1 is equal to 1 times A equals A, which is what the example I just gave in using the number 4. 4 times 1 is the same as 1 times 4 is actually equal to 4. In this section, an identity matrix I is identified that has the property similar to those of 1. Okay? If I is to be an identity matrix, then the products matrix A times I and I times matrix A must both equal A. An identity matrix is a matrix that has ones on the downward diagonal, starting at the upper left and going to the downward right. These are all square matrices. The downward diagonal are all ones and everything else are zeros. Okay? So if we take a matrix that has elements A, B, C, D, times the identity matrix, which is a square matrix of the same size, we can do the math, and we get, for this first one, row 1 times column 1, we get A times 1 plus B times 0, which you can see there, which is simply equal to A. And we can go through all of those and see that we get the same thing. Matrices, in order to have an inverse matrix, or let me continue on without holding that thought for a minute. So again, an identity matrix, this is a 3 by 3 identity matrix. Notice again, the ones are on the downward diagonal and everywhere else is zeros. Identity matrix is a square matrix with ones on the downward diagonal and zeros everywhere else. Okay? Here is a 4 by 4 identity matrix. These again are always square matrices. Recall that for every non-zero real number A, the equation AX equals 1 has a solution. Namely, x equals 1 over A, or A to the negative 1, which is really the inverse of A. Okay? Similarly, for a square matrix, we consider the matrix equation AX equals I. This equation does not always have a solution, but when it does, we use special terminology. If there is a matrix A to the negative 1 satisfying A times A to the negative 1 equals I, then that matrix A to the negative 1 is a solution of that equation we just mentioned, and a to the negative 1 is called the inverse matrix of A. It is very important that you recognize that this inverse matrix is not the same as the inverse of A, which was just changing the sign of every member in A. That is not what the inverse matrix is. An inverse matrix is a special matrix that when you multiply a matrix times its inverse, you get the identity matrix associated with that. Remember, the identity matrix is 1s on the downward diagonal and 0s everywhere else. Be careful, only square matrices have inverses, but not every square matrix has one. A matrix that does not have an inverse is called a singular matrix. And note that the symbol A negative 1 does not mean 1 over A. It is not a negative exponent. It is simply notation. Given matrices A and B as follows, determine whether B is the inverse of A. Okay? If B is the inverse of A, when we multiply A times B or B times A, we should get an inverse matrices, which would be 1 on the downward diagonal and 0s everywhere else. So let's multiply A times B. When we multiply A times B, and you can plug these in your calculator, matrix A, matrix B, multiply them, you should get the inverse matrix. Again, downward diagonal 1, 0s everywhere else. We have to also check BA to make that sure that's true, because if it's an inverse, the order will both result in the inverse matrixing. When we do that, we also get the inverse, and so we can see here that indeed B is the inverse matrix of A. Now be careful. Now, remember what I said, it's confusing because we had inverses of a matrix before, and this is the inverse matrix. An inverse of A is just changing the sign of all the letters, but B is the inverse matrix of A, which is a totally different. Notice that it's not negative 1 in this first position, it's negative 3. Find the multiplicative inverse of A. I'm going to go through this really quickly because your calculator will do this, and I don't expect you to go through this kind of process. So if we're trying to find the multiplicative inverse, the other inverse was the additive inverse, and the inverse matrix of A. What we're going to do is create a matrix with all variables. Okay? That will be our inverse of A. And we know that if we multiply A times the inverse of A, we should get the identity matrix. Or if we have A times the inverse matrix of A with all these variables, because we need to know what each element is, we should get this matrix. So what we can do is if we multiply through, notice that we're going to get a whole bunch of equations. So for example, 2x plus 4z equals 1. 2y plus 4w equals 0. X minus z equals 0, and y minus w equals 1. Now how do we get these? Well, these are just the multiply, right? 2 times x plus 4 times z equals 1. So we can change all those equations, these two matrices, since they're equal, we can set each of the elements equal. Row 1, column 1 equals 1. Row 1, column 1, row 1, column 1. Row 2, column 1, row 2, column 1. Row 2, column 1, row 2, column 1. All right. And now we have enough equations that we could start solving. Here we could solve for x, and then plug that in up here and solve for z. Or we can do augmented matrix and solve them the way we did before. Okay? So when we do that, we get the inverse matrix of A equals 1, 6, 2/3, 1, 6, negative 1/3. Again, you can write each of these as matrices. Remember, we did that before and then went to the RREF function to find the answers, and that's what's done here. Okay. So we can also use our calculator to find the inverse, and this is what I expect you to do. Okay. Enter your matrix into the calculator, 1, 0, 1, 2, -2, -1, 5, 0, 0, and this is a 3 by 3 matrix. And then use the x to the -1 key, which is right by the matrix button, to find that. So enter your matrix, exit out, go back and select the matrix, and then hit the x to the -1 key. And you can see here that it will give you the answer. So we get 0, 0, 0.2, -0.5, -0.5, 0.3, 1, 0, a -0.2. So your calculator will find the matrix for you. If we do the same thing with B and try it, you should get an error. And notice the error says singular matrix. Well, remember, a singular matrix is one that does not have an inverse. It is square, so it potentially has an inverse, but in this case it doesn't, and this is the error message that you'll get. So that's the end of our lecture for 6.5. Hopefully this is helpful. There's some confusing parts in here, but you can always go back and review again.